Hello friends, Alessandro Domenico Calvi, welcome back to the Scientific Moment. This transmission is coming to you from the eastern lowlands of cloudy Scotland. Today is the 17th of April 2018. Now, as I had already anticipated in a previous video, this is the third and final, at least for now, installment of the annual Scientific Moment presentations. And this one is about CO2 capture, broadly speaking. At the time, I was a PhD student in carbon dioxide capture, and so my friends had asked me to do this presentation at the Scientific Moment conference. So this is that presentation and a few extra slides that I have added, so I hope you enjoy this one. So, CO2 capture, climate savior. We shall see. Objectives and the overview of today's presentation. So the first thing I want to do is take you through the rationale for having CO2 capture as a technology and how it works, generally speaking. So between the capture, transport, and utilization or storage of the carbon dioxide. A quick case study of the Boundary Dam. The Boundary Dam is a coal power plant in southern Saskatchewan in Canada, and I've been there in 2016, so I will show you a few things that I found out over there about the first, well, one of the largest commercial projects of CO2 capture that has been done so far. Then I'll just broadly take you through some of the research that I did at Heriot University and the limitations of CCS as it stands and why it hasn't been adopted more widely, and then we can evaluate how effectively this technology can reach its stated goals of climate protection. So, climate crisis. CO2 has been identified as one of the main problems in our society so far. Rising global temperatures and climate stability, so flooding, droughts, glaciers melting, hurricanes, and other kinds of sporadic weather events, which have both been increasing reportedly in frequency and magnitude. And therefore, the United Nations has set as one of the goals for the sustainable development the reduction of our carbon footprint. Now, I don't want to go in depth with the discussion of the validity and sort of effectiveness of this plan, and I'll try and keep my politics to a minimum in this presentation, although I think it would be very informative and interesting to actually go through to what the premises of this entire field are in a more critical sense. But it won't be in this presentation. So, CO2 capture and storage, what is it? Well, broadly speaking, it is simply a method of prevention, so preventing that CO2 is emitted into the atmosphere. And this can be done in three broad ways so far. So post-combustion, pre-combustion, and oxy-fuel, also known as oxy-fuel combustion, capture. And it's quite self-explanatory. Post-combustion CO2 capture separates and stores the CO2 after the combustion of the fuel in air, and then it is compressed and dehydrated and sent on its merry way to wherever it's going. Pre-combustion CO2 capture gasifies the fuel in some sort of pyrolysis reaction, which means that it is heated in the absence of oxygen to release the compounds that are in the fuel, and those are then separated out from CO2 and the rest, and that fuel is then burned, and it usually is hydrogen, so mostly hydrogen at least, and you will not get as much carbon dioxide emitted because it has been already removed prior to the combustion process. Oxy-fuel entails separating the air with which the combustion is undertaken prior to the combustion process, and what that does is vastly increase the CO2 concentration in the flue gas. So usually there isn't a further separation step required, as you'll usually get around 90% or, well, 80 at least, depending on the type of process. So you will probably need an extra separation step, but it's much smaller, at least in terms of volume and size. So that is the advantage of that particular process. Now, so the applicability of carbon dioxide capture, as we've been seeing, it's mostly just fuel combustion, and therefore it is mostly applicable to large-scale single point sources, and not very much, in fact, at all, at least so far, been used for any kind of distributed source. I mean, even humans are kind of a distributed source of carbon dioxide. So this is the boundary dam in Canada. This is the power plant, the coal here in the background, the big mound, and this is the capture facility. Now, what's interesting is that the whole power plant is of 670 plus megawatt electric power output. However, the capture facility, and this is the capture facility, this is the amine unit for the sulfur, and the secondary unit is for the carbon dioxide. This facility is only for the third unit, which has been renovated at least relatively recently, and that's why the capture has been implemented on that kind of system. However, it only serves less than a quarter of the whole power plant, so that's very interesting to note. And then, of course, just for scale, the cars here. The three main products of the boundary dam are fly ash, which is precipitated electrostatically from the flue gas, and that it can be sold as a concrete aggregate to the sort of civil engineering industry. Supercritical CO2, which is the main product of the capture, is used for enhanced oil recovery in North Dakota. So that's pumped down across the border to North Dakota, and is sold over there. The sulfuric acid is also generated from the sulfur that is captured from the flue gases, and that also can be sold on a commercial scale. So what are the challenges? Well, this is me here in July 2016. It was wonderful weather there in Canada, and we had quite a few discussions about what the general challenges to more wide application of CO2 capture. Now, one of them is the reduction of the plant footprint. As we said, the size of the facility is quite large with respect to the rest of the plant, especially if you need to capture for the whole plant. And that can be a major problem, especially for retrofitting on power plants, which last many decades. So if anything needs to be viable, it has to be done via retrofitting as well. Another one is the reduction of the parasitic load. So essentially the parasitic load is that energy that needs to be inputted to run the secondary plant, and that's not just to run the whole control systems and just the whole building, but mostly the heat that is required to regenerate the sorbent, and we'll see that further what that actually entails. And in this specific case, it is approximately 12 to 13% of the overall steam output of the unit is being used as heat to regenerate the sorbents. So you have quite a lot of economic opportunity cost, which is the lost output, the lost sales of electricity that the plant has to endure to do the capture of the CO2. And that's just to say that the CO2 demand may not be even stable. So the design of the reactor, the design of the boiler was done in such a way that the CO2 could be variably asked for. So if the CO2 plant had to be shut down, all the steam could be used into the generator. However, at least at the time, since the beginning, the CO2 has always been pumped on maximum. But that at the same time, they've had procured a large steam turbine, which doesn't even operate at full capacity. So that's one of the economic kind of trade-offs you have to undertake. And so far, at least until then, the demand for CO2 was always at its maximum, but that can always not be the case, and it could be variable. And so just overall is the reduction of the economic burden of CO2 capture to make sure that the companies and the free market can take care of this problem without too much government subsidy or intervention. So this is the pipeline that's next to the capture facility at the Boundary Dam, which ships all the CO2 that is captured. Just this one relatively small pipeline, if you think about it. And some of it was also sent to the Aquistore storage and monitoring facility, which is very interesting. It's undertaking some geological research and kind of the seismic activity of the field as you keep injecting CO2 and monitoring that kind of aspect. So very interesting research for sure. And we did visit, but it was not operational at that time. As we said, most of the CO2 was being sent to North Dakota. And this is the map. So Saskatchewan is here, south of the southern part of Canada. This is the northern part of the United States. And this is Regina, where I was staying at, and a couple hours of drive south is where the Boundary Dam is. And across the border into North Dakota was where the CO2 was sent. Now, just for representation's sake, this is the kind of storage site you'd be looking for to store CO2, which is a porous and permeable rock underneath a cap rock, which is non-porous and non-permeable. So what you can do is you can pump the CO2 down here, and it would not be able to rise back up because of the non-permeability of the cap rock. So it'd just be buoyant. And just to give you a sense of scale, so this is the power plant here, and you can see that there in a larger zoom. And this is just how deep the pipelines go. It's quite deep with respect to what we are used to, kind of digging in the sand at the beach. So this is the production of oil in barrels since the mid-50s, and we can see that as you get technological breakthroughs, you get a different kind of peak in the oil production. And CO2 EOR has been done for quite some time now, possibly the early 2000s, and that's because there are also naturally occurring supercritical CO2 pockets in the geological kind of structure of the Earth, and companies will be able to use that, could just drill, get the CO2 from there, and use it for their enhanced oil recovery. So it is a technology that has been used in the past, even without the CO2 being directly captured from a combustion process in a coal power plant. But now that we've had this breakthrough, the CO2 may even be cheaper to source for these companies from other companies, which is interesting. So supercritical CO2 is a very good solvent, and what the solvent does is reduce the viscosity of the oil which is in the field, and you can pull more out. The vast majority of oil in a field is usually never recovered, so I think it's something like 70 to 80% of the oil in a field never leaves the field, and so the maximum you can hope for is that 20%, and enhanced oil recovery will just increase it by a couple of percentage points. I guess I'm not in this field as much as I was in the CO2 capture generally. So the main criticism here is that you're basically turning a concentrated emission that's being pumped into the ground into a distributed emission by having the oil extracted and used possibly through refinement for cars, ships, planes, etc. So the research at Heriot-Watt, it was to do with a microwave swing adsorption of activated carbon. So microwave swing adsorption is simply a type of thermal regeneration. So as I was saying, steam is required to heat the adsorbent, the absorbent in that case, to regenerate it. But in the case of my research, it was using a microwave system. So activated carbon is a type of sorbent which is quite versatile. So its porosity has is quite broad. The pore size distribution is quite broad. And what that means is that a large different types of molecules can be trapped in its kind of micropores, and this is positive for example, environmental cleanup, heavy metals, and even pharmaceuticals, other kinds of pollutants that are found in the water supply can be removed using activated carbon. Activated carbon is very cheap, so in this picture, it is from this EcoPlanet bamboo company, which makes it out of bamboo in South Africa. But I was sourcing mine from coconut and almond shells. So it's usually just food waste, very cheap and very versatile. The problem is that if you are looking to specifically capture CO2, you have this problem where if you're capturing a wide variety of molecules, then when you are regenerating your sorbent, you are not getting just pure CO2 into your new stream, which is supposed to be supposedly purified. It will be especially filled with water, which has a high affinity for activated carbon. So that was one of the drawbacks. But it was very cheap, and it was very interesting to do research on this kind of compound, solid. So I've done, this is I'll show you the research that I did between October 15 and February 2017. So first of all, we can start with what absorption is. So the difference between absorption and adsorption is that in absorption, the molecules bind to the bulk of the solvent. And by bulk, we mean the whole mass of it. So if we can imagine a liquid which has an interface, the CO2 would diffuse through the interface into the bulk of the liquid. Whereas adsorption, it would just be the sticking of the CO2 to the surface, to the interface. Now, generally speaking, there is no, absorption is mostly a liquid thing or a fluid thing. Even gases can be absorbents, but adsorption is more of a solid thing because it has a well-defined surface. And of course, activated carbon being microporous has a lot of surface area internally, which allows that. So just to see the animation, you get in the jars, you get into the bulk or just onto the surface. In fact, I should probably have put these molecules on the outside of the jar because they don't actually enter. Let's just watch the animation again, and that's how it is. And that's the difference between absorption and adsorption. Now, the other thing that we can look at, so the same as absorption, adsorption occurs at a certain bulk condition. So at a certain temperature and pressure, you have a certain absorptive capacity of your sorbent. And this can be reversed by temperature or pressure swing adsorption. So if we can make just a practical example, here we've got Q, the absorptive capacity of the sorbent, and two isotherms at a hypothetically low temperature and a hypothetically higher temperature, and this is the relative pressure of what's in the system. And relative pressure can also just mean the percentage of CO2 in the flue gas. So we can start with a relatively low pressure system, which through the absorption is compressed. So via the compression, the high pressure in the system increases the absorptive capacity of the sorbent, so it gets saturated at a higher rate. And then once you decompress it, you can release the CO2 somewhere else. And similarly for thermal swing generation, if you have a high temperature, it will you'll absorb at a lower temperature, and then by the regeneration, you by heating it, you will release the CO2 again. And those are the two main processes. So the heat, it comes from the steam in the case of the boundary dam. In my case, the microwave system, which you'll see in a sec. The overall process, and it has changed over time, but this was at the time the process that I was using. A degas, so heating the sorbent in situ, so inside the glass vessel, heating it up, make sure that all the impurities were kind of boiled off, and then you could start the absorption process, so having the gas flow on top of it at the ambient conditions. Then a purge. I was doing this simply to improve my measurements on the mass spectrometer, but this step was later removed, and I would not purge. In fact, the purge, it would mostly just be the desorption process with a slight flow of nitrogen as a kind of cleansing gas, or just to push the stuff along. And the desorption was at 130 degrees or 70 or 90. I was doing different kinds of experiments, and then cooling. So once it's cooled, you can go back around and go full circle, and that would last for 60 minutes, which is a considerable downtime considering the speed of the other two processes, especially adsorption and desorption. This is the whole overall setup. So the gases would come here. These are some pressure regulators coming into this rotameter, which has a mixer, and this would you can regulate the ratio of CO2 and nitrogen coming in. So it was a surrogate gas. It wasn't real exhaust gas, but you could simulate at least the two main components, which are nitrogen and carbon dioxide, coming through here into the adsorber, which was placed into this column, which is inside the microwave system, and the microwave is the main source of the heat, which is controlled via a proportional, integral, and derivative temperature controller, which is here, which is connected to an infrared pyrometer, which can sense the temperature of the gases down there. So that by this control loop, you could control the desorption process. Then the gases come out here, and they get measured via this Coriolis meter, which measures the mass flow rate, and then via a GC column into the time of flight mass spectrometer, which basically could measure the relative concentration of, well, at least the relative frequency of the ions hitting the detector of CO2 and nitrogen, and then that would just go to the exhaust into the atmosphere. This is the same diagram of the system, but just in a more technical format with the piping and instrumentation. As I said, just mixers coming in. You've got the stuff inside the microwave cavity, and then the computer controlling some things, and then the exhaust to the atmosphere. These are some of the results. So the blue line is the concentration, the yellow is the mass flow, and this is the time elapsed of our experiment. So in the beginning, you'll get negative concentration because you're having some net absorption at a relatively high flow rate. In fact, here you get a dip because a certain percentage of the flow is carbon dioxide and not going in. Here it's 5%, and you can see it's approximately a 5% dip in the flow rate. Then once the absorption is completely saturated, so you see there's a breakthrough here, and then you have 5% gases just flowing straight through. Then you can bring down the absorption, so the heating turns on here, and it essentially goes really fast to a higher temperature. And you'll see this is the usual flow rate of the nitrogen should be down here, but you're having this extra bump of flow which is coming out directly from the sorbent, and a spike of concentration. So there are quite some limitations, because I mean the nitrogen-rich nitrogen-rich flow that's coming out already from the system is being diluted, is diluting the supposedly almost pure CO2 which is coming out from the sorbent. So that's unfortunate that we can only reach 25% purity in this kind of experiment. So this was this one experiment at 5%. With a 30-degree absorption and a 70-degree generation. So it was quite interesting. I presented this work at the ICCDU, the International Conference on Carbon Dioxide Utilization in Sheffield, and they liked me so much that they gave me quite a nice prize, and I was quite chuffed about that one. So then the cost of carbon dioxide and microwave single absorption. So overall, we haven't really costed the microwave system. And it definitely does seem quite expensive if you think about what kind of equipment you'll require and where you're going to put it for your plant. But we didn't really evaluate it in that sense. So the size and the cost of implementing CO2 capture in general is quite high, but in terms of the microwave system could even be not viable, at least for now. Yes, so the products that are generated from CO2 capture, so namely the fly ash, it's the fly ash you could get possibly anyway, but whilst you're doing all this, the sulfur and for the sulfuric acid and the carbon dioxide definitely reduce the cost and then try to offset the cost of what the CO2 capture removes from the electricity sales. So CO2 capture is a large investment, and so for now it looks like only large players with which do enhanced oil recovery are able to at least afford to pay out the price of the capture of the CO2 indirectly via their commerce with a plant that does the capture. The oil price instability as well. I mean that's a major issue, because this graph is not linear. But at least at the time when I went there, the oil prices were terribly low, and that's why they were worried that they would reduce their demand for carbon dioxide capture, the captured carbon dioxide for the oil recovery, because it reduces the incentive of recovering oil if your costs are not recovered. But it seems like in recent years, at least since then, the price has gone up again a bit. It hasn't really recovered to the levels of before, but that is simply that problem. So the EOR is only financially viable way to integrate CCS in the fossil fuel chain for now, and if the prices remain low, then or even unstable, it makes it difficult for the market to bring some investments in the long-term solutions. And it is important that the market picks up on these things, because you will never be able to rely on a government subsidy forever. I mean, it was very good that the Boundary Dam was able to secure some funding and some help in different ways to offset their research costs and make sure that the business can take some more risks. But then after that, if the market makes it profitable to capture CO2 and possibly just store it underground or do something else with it, then that would make a big make a huge dent to the CO2 emissions, because now from being a waste product it becomes a resource. So it is important to think about how the free market will solve this problem. And so far, the oil price instability does not help, at least the niche market which it is operating in. So the conclusions for today. So CO2 capture has been marketed as an idea for emission reduction, and this certainly does reduce the emissions of the power plant down below the level that was legally allowed in Canada. So that's positive, but we'll have to see what happens to the whole chain. Purifying the CO2 is quite costly and difficult, so you don't want to just store it underground, ideally, because then the market will never take over in that sense. And so the only economically viable option for now is EOR, and as we see, I did criticize it a bit because it does just put the CO2 back into the atmosphere one way or another, and it is displacing the single point emissions into distributed. As the oil prices were low, the incentive for EOR was very low as well, although we're seeing it going back up, so we'll see what happens next. The field is very large. Like there are many aspects of carbon dioxide capture which I didn't discuss, but I mean, if you're interested, I'd be happy to discuss it in the comments below, or anywhere else. There's definitely other things that can be said. These are the few references. Not all of them are very important. I think the most important one is this one here, which is the IPCC third assessment report, or at least the section on carbon dioxide capture of the Intergovernmental Panel on Climate Change, which is the UN's panel for climate change research. I would recommend, you could probably find it online. So if you're interested in that, please do read it and criticize it all you need. The more criticism we have, the better we can move forward. So if you're interested in seeing more of me, my main channel I'll be trying to upload to is BitChute, especially because I don't even know what's going on with YouTube these days, with all the messes they're making. And same with Facebook. I'm trying to get off Facebook, and I'm on Minds. Whether I'll be using Steemit or not is we shall see in the following weeks and months. I have an account, but I have not yet posted anything on there. Okay, well, so I hope you enjoyed this video. As I said, if you do have any even rebuttals, things that you don't agree with, or perhaps more clarification, I would quite happily take your comments in down below, or even private messages on these accounts that I've just shown you. Well, from the eastern plains of the lowlands of Scotland, it's been wonderful to speak to you, and I hope you have a wonderful rest of your day. Goodbye.